In this lecture, we're going to define a simple truss and identify zero force members. Truss structure is widely used in construction, especially in bridges and roofs. You have probably seen many truss structures in your everyday life. For a given truss geometry and load, how can you determine the forces in the truss members to be able to select their sizes? A more challenging question is, for a given load, how can we design the truss's geometry to minimize the cost? So there are two methods for simple truss analysis, the method of joints and the method of section, which we will discuss later. And now let's take a look at what is a simple truss. First, let's give truss a definition. A truss is a structure composed of slender members joined together at their end points. So you can see those slender members and the joints. And in most of the cases, those joints are joined by pins, pin connection. If a truss, along with the imposed loads shown here, lies in a single plane, then it is called a planar truss. And for a planar truss, if it's only composed of triangular elements, then it's called a simple truss. So a simple truss is a planar truss which begins with a triangular element and can be expanded by adding two members and a joint. So again, it's only composed of triangular shapes. As we mentioned earlier, when designing the members and joints of a truss, first it is necessary to determine the forces in each truss member. And this is called the force analysis of a truss. And there are two methods for simple truss analysis, the method of joints and the method of section. And we're going to discuss them later. And here is a picture of a model truss bridge, which is built with only slender beams. Let's analyze this bridge span. It consists of a back panel and a front panel. The back and front panels are connected with floor beams. And on this floor beam, we can add a deck. And this is the surface to provide support to the cars or train that cross the bridge. Then on the deck, assume we have an arbitrary loading, look like this. Because the deck is built on top of the floor beams, and this distributed load is now translated onto those floor beams. And the floor beams are connected to the joints of the back and the front panels. Therefore, the loading is further translated to the joints. And it is supported by the bridge piers. And this leads us to the idealization assumptions we make for truss analysis. For simple truss analysis, three assumptions are made. First, simple truss is constructed by expanding triangles. And in fact, in this class, we further limit to 2D truss structures. Once you've learned this, you can expand the application to space truss or other 3D truss structures. Second, all loads are applied at the joints. So you will not see loads applied on the members. The loads will only be applied to joints. And the weight of the truss members is often neglected. 3. The members are joined together by smooth pins. Between the members, there will be a smooth pin connection. And for the supports, the entire structure will be supported by pin supports. So on the left, we have the roller pin support, which only exerts one support reactions that is perpendicular to the contacting surface. On the right, we have fixed pin support, which exerts two support reactions, one horizontal and one vertical support. Because of the assumption that forces are only applied at the joint, and the joint are located at two ends of the truss member, and this makes the truss member a two-force member, since forces are only applied at 2 points of the member. And for two-force members, we know that the two forces must be along the same line of action, which is the line connecting the 2 points. And the forces must also have the same magnitude, but opposite direction. And for each force, for the truss members, there are only two possibilities. Either the forces are pointing out into opposite direction or pointing into the member. So if the forces are pointing out, try to stretch this truss member, then the force is called tension or tensile force. If the forces are pushing into the member, it's called compression or compressive force. So that means in a simple truss structure, the forces developed in those members are either tension or compression. To solve simple truss problems, we have two methods. The first one is the method of joints, and the second one is method of sections. So let's take a look at method of joints first. First, imagine several truss members, 4 truss members are joined by a pin here. When forces are applied, the pin will exert forces on each member. So for convenience and to see those forces, let's imaginarily separate the pin and the member so you can see the force distribution or the force on each member. So the force F1 is the force exerted by the pin on this member. Force F2 is also the force exerted by the pin on the member 2, and force F3 and F4 respectively. And our goal is to solve the force F1, F2, F3, and F4 exerted by the pin on each member. And now we're assuming all the forces are in tension because it's going outward from the end of the member. Because of action and reaction, the truss members also exert forces on the pin. So the force showing in the red color, those force vectors, are the forces exerted by member on this pin. So F1 is the force exerted by this member 1 on the pin. F2 is force exerted by member number 2 on the pin, etc., etc. And because of action and reaction, those forces are of the same magnitude. Therefore, if we want to know what the forces in the truss members are, we can simply solve for the forces acting on the pin instead. And because this will become a particle equilibrium problem, pins can be considered as particles. And for planar, this is the focus of our class. We're going to solve 2D or planar simple truss. We can apply the 2D particle equilibrium to each pin. Again, instead of analyzing the member, we're going to analyze the pin, and we're going to treat the pin as a particle and apply particle equilibrium to each pin. If the forces in the members are tensile or in tension, then the forces acting on the pin pull away from the joint. If the forces in the member are compression, then the forces acting on the pin push towards the pin. This is the base for the method of joints we will discuss later. Let's see one quick example, the method of joints. Assume we are looking for the force developed in the truss member AB and BC. Instead of using AB and BC or treat AB and BC as rigid body, we are going to use pin B instead. So pin B can be simplified as a particle, and we're going to perform the particle equilibrium. Draw the free body diagram of pin B or joint B. So when we draw the free body diagram, we need to isolate this point B from the surroundings, but place the force exerted on the pin B. We need to identify all the external forces, including the 500 Newton force, the force exerted by the member AB, and the force exerted by member BC. And after writing this free body diagram, we have two unknowns, FBA and FBC. And we know for a 2D particle equilibrium problem, we can write up to two equilibrium equations, and we can solve those two unknowns. In comparison, let's also take a look at the method of sections. So for method of sections, if this member is in tension and we're looking for the force F, we run an imaginary cut through the beam. And now we expose the internal force as externals. And if this member is in equilibrium, and then any segment from the member is in equilibrium. So if we take a look at the left segment, this segment must be in equilibrium. As a result, the internal force F must be equal to the external force F, and it's also a tension. Same idea for the right segment. It must be also a tension force has the same magnitude F. And if the member is originally subjected to compression, has a parallel force, pushes into both ends, we run an imaginary cut through the member at any location. And again, the internal force will be exposed as external. And because of equilibrium, we can see those forces are the same as the applied force at the end. And this pair will also be compression. So we can say the force developed inside the beam is the same force everywhere, same magnitude, same tension or compression. And this is the base for method of sections. For this simple truss structure, notice at joints D and E, there are only two truss members connecting to it with no external loadings. Let's apply particle equilibrium at D and E separately. First, for pin D, I set up the XY axis with D at the origin, and then let's draw the forces applied at pin D. So here one is the member AD or DA. So let's assume DA has tension developed in it. So if it's tension, then we'll also pull away from the pin. So we'll call this force FDA from D to A. And also for the other, there's another member DC connecting by the pin. So there will be a force exerted on this pin by this member DC. And we assume DC is in tension as well. So we'll pull away from the pin as well. So this is FDC. Okay, so that's the only two forces applied at pin D. Now use the equilibrium equations. Sum of x equals to 0 and sum of Fy equals to 0. We can get, well, along the x direction there's only one force, which means FDC must be 0. And along the dA direction, there's only one force, or y direction, there's only one force as well, which is FDA. So both of the forces are 0. So that means there's no force developed in the member CD or DC and DA. Let's take a look at E. Set up the XY axis and then put the external forces on E. First is this EB member will exert a force on pin E. Let's assume it is also in tension. So we'll pull away from the pin E. Let's call that FEB. And there's another force along the member EC. Assume that is tension as well. So pull away from the pin E. So this is FEC. Same idea. Those are the only two forces applied at pin E or joint E. Let's write the equilibrium equations. So along the x direction, we have only one component, which is the x component of this force, FEC. Therefore, FEC has to be 0. And when FEC becomes 0, from the second equation, we can see this force FEB will also be 0. So that means in the member EC and EB, there's also no force. And those members with no force developed in them are called zero force members. And we can remove them from the structure before doing analysis for other members to simplify the problem. So to summarize the zero force members, this is one type of zero force member. If a joint has only two non-collinear members and there's no external load or support reaction at that joint, then these two members are zero force members. And I already did the example at pin D and E, and those members are zero force members. And zero force members can be removed when analyzing the truss. So after we identify the zero force, we remove it from the structure. Now the structure is greatly simplified. And there is another type of zero force member. Something look like that. At pin D and pin C, there are three members joined by the pin. If three members form a truss joint for which two of the members are collinear, means along the same line, and there is no external load or reaction at that joint. So again, there's no external force applied at the pin, or there's no support at the pin. Then the third non-collinear member is a zero force member. So the third one is the zero force member. So in this case, AD and AC are zero force members, and we can remove them from the structure to simplify the problem. Please note that zero force members are used to increase stability and rigidity of the truss and to provide support for various different loading conditions. And when we say this is zero force member, it's only valid when it's under certain or the current loading status. So if, for example, in some of the cases, there is a force applied at pin D, then the member AD is no longer a zero force member, because zero force member requires there's no external force applied at the pin. Same idea for this pin C. If we we have an applied force applied at pin C, then this member AC is no longer a zero force member. Let's take a look at the steps for analysis. First, draw the free body diagram of a joint with one or two unknowns. So keep in mind, this essentially is a particle equilibrium problem, and it's a 2D particle equilibrium. We can only write a maximum of two independent equilibrium equations and solve up to two unknowns. So if you have more than two unknowns at one joint, then we don't have enough equations to solve it. Assume that all the unknown member forces act in tension. They are tensile forces, unless you can determine by inspection that the forces are compression loads. So keep in mind, you have to draw the free body diagram of a joint to solve your problem. The second step is to apply the scalar equations of equilibrium. We have two equations, sum of fx equal to 0 and sum of fy equal to 0, to determine the unknowns. Repeat those two steps at each joint in succession until all the required forces are determined. And if the truss support reactions are needed, we need to apply rigid body equilibrium for the entire truss to determine the support reactions first. However, this step is only necessary when we need to know the support reactions. Example 1. Loads as shown on the truss, and we're looking for the forces in each member of the truss, meaning we're looking for forces in AD, CD, BD, AB, and BC. So first we see this is a simple truss, and we're going to apply the method of joints. And the question is, which joints are we going to start with? But first, we need to identify, is there any zero force members, so we can remove it to simplify the structure. Now we can see that at pin B, there are three members joined together, and with two members are collinear. So the third member that is not collinear is a zero force member. So we can then remove it from the structure. And now we can think about which joint do we start with. Keep in mind, we are looking for a maximum of two unknown forces. If we have more than two, then we cannot solve it. Well, if you take a look at pin A, for example, we have AD has force applied at pin A. We have AB applied on pin A. We also have the support reaction from the ground. So it has three forces. Plus, we do not know the support reaction, so there's no way we can solve it from A. Same idea at pin C, and even at pin C we have one more reaction because this is a fixed pin. There are two supports by this pin, smooth pin at pin C. Well, but if you take a look at pin D, since we already removed this member BD, there are only two members now connected at joint D or pin D. One is the member AD and one is CD. And then the applied force, which is 450 pound force. So there are only two unknown forces. So we'll start from A, and after we will start from pin D, and after we solve D, the force in member AD will become a known value. Then we'll reduce the number of unknowns at pin A from 3 to 2. Then we can solve all the unknowns at A. So after this quick analysis, we're gonna first apply the method of joints to pin D and then pin A. And then we'll see if it's necessary to move on to pin C. And now the question is, for this problem, do we have to find the external reactions before solving the problem? Well, for some problems, we do need to find the support reactions because we don't have enough known values to solve the forces in the truss. But for this one, after our quick analysis, seems like, again, when we start with pin D, we can solve AD and CD already. And now at pin A, we only have two unknowns, which is AB and the support reaction from the ground, NA. And at pin C, we already solved CD with pin D, and we just have one more left, which is BC. So that means the support reactions are not necessary. Okay, so let's write them down. First, as we mentioned earlier, we're going to start with pin D. So the first step is to draw the free body diagram of pin D. Well, before that, let's mark BD as a zero force member. So we're going to remove it from the structure. So we're not going to have BD in our free body diagram of any joints or any pin. So let's draw the free body diagram of pin D. So please, when you write your homework, work on your homework assignment, draw the free body diagram of each pin separately from the original figure, because you're going to draw the free body diagram for each pin. If you use the original figure, pretty soon it will be very messy. Okay, the first step, my suggestion is put the XY axis is if it's not given, because we need to build the equilibrium equations and it's based on the x direction and y direction. So it's important to have XY axis. All right, so pin D is located at the origin of this XY axis. And now there is one applied force, which is 450 pounds to the negative x direction, pointing to pin D. And the member AD will exert a force on pin D since it's an unknown force. So FDA is unknown. So we'll assume it's a tension. So if it's a tension, we'll pull away from the pin D. So that's why this force is along the direction of the member AD and pull away from the pin. Same idea for this member CD. The force exerted by the member CD on pin D, and we assume the member CD is in tension as well, so it's pulling away from the pin D. And put angles on your free body diagram to help you write the equilibrium equations. Now again, if we check our free body diagram, we have only two unknowns, FAD and FCD. So with the two equilibrium equations, one is in the x direction, one is in the y direction, we can solve two unknowns, FCD and FAD. And in solving those problems, simple truss problems, we all know that those truss members are two force members. The direction of the force must be along the direction of the member. So for example, FAD must be in a 45 degree with the x-axis. Same for FCD, must be in this direction. But in the answer, we need to indicate two things. One is the magnitude, two is tension or compression. So when we solve those two equilibrium equations, FCD is solved to be positive. So we assume CD is positive in our free body diagram. So if the answer is positive, so sorry, I said when we on the free body diagram, we assumed FCD is in tension, and we assume FAD is also in tension. So our solution shows FCD is a positive. That means our assumption is correct. So FCD is in tension. On the other hand, FAD is solved to be a negative value. So that means instead of tension, it must be a compression. Okay, so that's why when we draw our free body diagram, we always assume those unknown values are tensions. So if the solution is a positive value, that means it is tension. If the solution is negative value, that means it is compression. And in your answer, you need to specify the magnitude and also tension or compression like that. From the analysis of pin D, we solved member AD and member CD. So you can put a mark on your diagram showing that those members are already solved, and you can use the value for the other pins. So next we're going to do pin A. And for pin A, we'll have FAD. Again, we already solved FAD from pin D, and FAD is in compression. The magnitude is 318 pound force. So recall that if the member is in compression, then you will push into the pin on both ends. So because AD is in compression, so it will push into this pin A, push towards pin A. So that's how you use the previous answer on this pin A. The magnitude is 318 and pointing to the pin A along this member AD. And next, you need to put the reaction from FAB and the support reaction at pin A, which is AY, normal to the supporting surface. And again, do not forget, before you set up the free body diagram, you want to draw the X and Y coordinates to help you write the equilibrium equations. And this is the free body diagram of pin A. And now we can check our free body diagram. We only has two unknowns, FAB and AY. But we are not asked to solve for the support reaction from the floor, right, AY. We are only looking for FAB, actually. So we just need one equation, which is the equation along the X direction to solve FAB. So FAB, again, this value, we assume it is in tension, so we'll pull away from the pin A, and then minus FAD times cosine 45 equal to 0. We solve FAB is a positive value, which means is in tension. And FAB is solved. FBC actually equals to FAB because we can use the equilibrium of pin B, and this is 0. If FAB is, let me draw a better one, pin B, free body diagram of pin B, X, Y, and B. Now we know FAB is tension, so we'll pull away from the pin B this 225 pound force. And for force BC, FBC is not known, but we're going to assume it's in tension as well. This is FBC. And that are the only two forces applied at pin B, since BD is a zero force member. So based on equilibrium, we can solve BC equals to 225 pound force, which is in tension as well. So all the members, 1, 2, 3, 4, we solved the forces for all the 4 members.